question. And the question that she asked was that how do we know the wavelength of a system, of a particle or matter? Of course we use the de Broglie relationship, this one. But how do we know the momentum of a particle? Let me give you a conceptual argument of the kind of things that we like to do. Suppose I have electrons which is ejected from a metal through thermionic emission. Alright? So suppose I have the photoelectric effect. I have the electron inside a metal. Now generally I used to teach photoelectric effect in the modern physics class, but now it's so simple that I don't teach it anymore. So it just comes as an A side. So suppose I have an electron inside a metal and light shines on this metal. Now light comprises of photons and each photon carries an energy hf, right? Where f is the frequency of light. And suppose this hf equals this is energy, right? So suppose this equals W plus K. Now what is W? W is the work function of the metal, which means the minimum energy required for an electron inside the metal to hop to the surface of the metal and become free, so that it goes out of the confines of the metal and it goes into air or vacuum. That's called the work function. Suppose the incoming photon has some extra energy over and above the work function W. That extra energy is K. So when the electron comes out of the metal, what would be the energy of the electron? K. Because it requires W to actually just barely escape. So with W it barely escapes, and anything extra over and above the work function that is imparted, given to the electron by the incoming photon, appears as the kinetic energy of the ejected photoelectron. Right? This is the photoelectric effect. The simplest description of the photoelectric effect. Now suppose that I perform an experiment in which HF is precisely equal to W. So what's the kinetic energy of the photoelectron? Zero. It just barely escapes. But it does come out of the surface. Suppose it's slightly a nudge above W, slightly above zero. So it has come out of the surface of the metal. Now you would like to accelerate this electron with the help of an electric field. So you apply an electric field in this direction, E, which means that the electron is accelerated. So if you have a positive plate, electron is sitting here at zero energy, zero kinetic energy, is going to be accelerated towards the positive plate. So you would actually apply an electric field to accelerate the electron. Now, as the electron is sitting and it starts to accelerate, it picks up energy, kinetic energy. And what's the amount of energy that it picks up? That's equal to the energy that the electron is gradually going to pick up is K equals the potential difference V, the charge of an electron, QV or VE, right? Now this is the kinetic energy of an electron. And if this is small, if the speed is smaller than the speed of light, we can use the formula that this kinetic energy is half mv squared. From this we can calculate the speed. V is going to be equal to 2k over m under root. This gives us the speed. And this gives us the wavelength. Lambda equals H M V. Now V is 2 K M. So lambda equals H over 2 mk. So this is how you calculate the wavelength of an electron moving with speed v or moving with energy k. Alright? Did I answer your question? In fact, this is a very important relationship. It's useful in understanding Bose-Einstein condensates, which is a Nobel Prize winning concept. So these simple concepts are actually at the heart of very exciting physics. Anyway, this is the intensity of the electrons that fall upon the screen. Now I give you a task. The task that I present to you is, does this intensity pattern correspond to this yellow interference fringes? Right? It must. That's the aim that we set out for ourselves. So the first question that I would like you to solve is, I would like you to make a graph of intensity IP versus the phase difference. Remember, phi is the phase difference. What is phi? Phi is this factor here. So what is phi? In English, what is phi? Phase difference between what? Between two waves, or the phase difference between two possibilities. The phase difference between two wave functions. So this is one possibility, this is the other possibility. And we're not prying open the apparatus so that we're trying to see which possibility that the electron is taking. We just let nature take its course and find out what happens on the screen in the final stage of the experiment. Alright? So this phi is what I call a relative phase difference. A relative phase difference between the two possibilities. Relative. So this is the relative phase difference. What I would like you to do is plot IP versus phi. Try to plot this relationship. If you've done the physics lab, you should be able to do things of this kind. Try to plot this relationship. Negative direction. Phi negative. Let me give you a suggestion. The suggestion is, you can first draw a graph of simple cosine phi, then draw a graph of cosine phi by 2, then square it. So let me plot the final result. Alright, so phi can be positive, can be negative, and this is the intensity pattern. This point is where phi equals pi by, so this is pi by 2 here. So if this is pi, we get this thing. This is minus pi. And so on. Now there are two nice things about this graph. Really nice. Three nice things. The first nice thing is that the pattern looks like interference fringes. What I intuitively drew on the blackboard last week and today. It has maxima, minima. It has bright and dark regions. Alright? So it has the correct form. It looks like the correct form. The second thing is that the intensity is real. Because it's a modular squared, it has to be real. And we live in a real world. Our detectors are detecting something real. They churn out numbers. They churn out counts of electrons, counts of photons. These are real numbers. Alright? So there should be nothing complex about it. The third nice thing is that the intensity is either positive, maximum, and the minimum is 0. There is no such thing as negative intensity. That doesn't make sense. The minimum of the intensity is indeed 0. Alright? So this mathematical relationship agrees astoundingly well with experimental observations. So this idea that particles are coming in, they are behaving like waves or fields, they are spreading out without actually splitting. The electron or the photon is everywhere inside the crater. It's taking out all of those possible paths. But you're not observing those parts. And at the end, there is interference between all of those possibilities. And on the end, when the final stage of the experiment is reached, on the screen you observe an interference pattern, which is explicable by noting that inside the crater there is a field or a wave, and it's interfering with itself. And this experimental result is also true if you have a single electron coming in at a time, a single photon coming in at a time. So this explains our experimental results astoundingly well. But an experimenter would actually not like to put phi here. What would he like to put as a variable here? What would he like to use as a variable? When you perform an experiment and you have a detector moving along the screen, what should you like to put here? The distance along the screen. So we have to find out the relationship between phi and the distance along the screen. So for that purpose, we can come back to this diagram over here, and we note that the phase difference can be found out in the following way. If I drop a normal to this path, this extra length is the extra path difference. Now if this angle is theta, and theta is small, which means that this is far away compared to this spacing, then this angle will also be theta under this assumption. If you're not too far off from the central axis. Correct? So this angle is theta. You can find out what this distance is going to be. This distance is going to be A sine theta. So this distance is A sine of theta. So now you have a distance. How do you get a phase from a distance? You multiply the distance with k, 2 pi over lambda. So this phi really equals k times A sine of theta. Now what is sine of theta? If you look at the diagram over here, this length, let's call this x. Let's call this distance capital D. You can find out what sine theta is. Sine theta is x over x square plus d square under root, right? Okay? So now you can also, if you like, you can convert theta into x. But I can plot this curve with respect, suppose theta is small. Let's do a simplification. If theta is small, which is my assumption here, then this sine theta equals tan theta. So I can equate this to Ka tan of theta. For small theta, sine theta is equal to tan theta is equal to theta. Almost. Now if you look at this diagram over here, what's tan theta? X over capital D. So my phi turns out to be K A X over capital D. Hence, if I were to plot, the intensity would now become IP K 2K or 4K cosine square phi over 2, which is K A X over 2D. Now this is 2 pi over lambda. So this becomes 4K cosine square phi AX lambda D. So if I were to draw a plot between IP and X, it will have the same form. Just the constants are going to change. Asan hai. This is simple algebra that I'm doing. There's a lot of steps, but everything should be crystal clear here. So if I were to draw a plot of the intensity versus X, I have X over here and I have IP over here. I will get a similar curve. Correct? Now what is this point over here? What's this point? Now I give you 2 minutes to think about this. I would like to find out what's the point of the first minimum on this side. Can you tell me what this point is going to be? Lambda d. Let's see. Now my question is, what I've done, I have plotted IP versus phi. But phi is, this graph is nothing wrong with it. It's a totally true graph. But I'm more comfortable drawing on the x-axis actual x, distance along the screen, because that's what I'm really observing. Alright? So I would like to convert phi into x. Alright? So what I do is I use the geometry to convert phi into x. And I get this formula over here. Now my question is, I would like to find out the minimum. Where does the first minimum in intensity occur? And looking at the formula, the first minimum in the intensity occurs where this object equals pi by 2. Now this object equals pi by 2 means pi ax, this is the minimum here, x, I call it x naught, over lambda capital D. I want this to be equal to pi by 2. This means my x naught is lambda D over 2a. What's this point? Minus lambda D over 2a. This point is going to be lambda D over a. 3 over 2 into lambda D over a, and so on. So at these particular points along the screen, I get a minimum in intensity. And if I have an ideal scenario, I will get 0 intensity. It's never going to happen, by the way. These fringes are never perfect. Excuse me. So now my question is the following. Let's call this central lobe the central maximum. So this is a lobe. This is my lobe here. Let's call it the central maximum. Now what factors does the width of this lobe depend upon? It depends upon A. If I decrease A, what's going to happen to the width of this central maximum? It's going to go up. Now what's my uncertainty? Or what is my, if I perform this experiment, what's my uncertainty in position? It's of the order of A. I don't know which slit the electron is going through. So I'm uncertain in the position by an order of magnitude A. Because I don't know which slit the electron is going through. The electron could be going through this slit, or it can be going through this slit. So my uncertainty, my indefiniteness about the position of the electron, I don't know the path of the electron, is of the order of A. I don't know which slit the electron is going through. So I'm uncertain about the position of the electron, and my amount of uncertainty is A. Alright? So if I decrease my uncertainty by moving these slits closer and closer together, if I move these slits closer together, I'll reduce the uncertainty in position. If this were just one slit of a certain width, my uncertainty would just be the width of the slit. Now if I reduce this, the central lobe is going to expand. So my uncertainty in the momentum is going to change. Now how is the width of the lobe related to the momentum? That's the question. Alright? So I'm going to explain that now. And I'm going to, so this is a slightly subtle concept, so I'm going to rephrase this. In the double slit experiment, I don't know the path of the electron if I were to see interference pattern. So the uncertainty I denote by delta. I have more to say about this uncertainty. I have a full lecture on uncertainty principle. But my uncertainty, my ignorance, or my indefiniteness is delta. And since I'm talking about position, it's delta x. So the uncertainty in the position is delta x. And how much is the uncertainty? My order of magnitude estimate is the separation between the slits. How far apart the slits are. Because I don't know if you're an electron and these are the two slits. And I don't know which door you're going out from. So I don't know your path. Alright? I have no means of knowing your path because I'm not seeing you walk up. I just see you where to get at the other side of the room. So my indefiniteness about your path spans the entire length of this room, that is the distance between these two slits. Okay? So my uncertainty in the position is of the order of A. This thing means roughly of the order of A. Now if I decrease this uncertainty, which means I move the slits closer and closer together, these points will go further and further out. So if I reduce A, which means I reduce this thing, which means I reduce the uncertainty in X, I become more definite about X. I increase my precision, quantum precision about the position, or I start getting some information about the path of the electron. Then what's going to happen is that these lobes are going to spread out. So the new pattern might look something like this. So this central lobe has expanded, has bulged out because A has gone down, the location of the first minimum has gone up. Now what does this have to do with momentum? I have to link this width of the central maximum with the momentum. Let me do that now. Yes. Good question. I was anticipating this question. Why is the intensity decreasing? Why have I drawn the blue curve to be shorter in height than the yellow curve? No. So this is thinking physically. Physics is not just about physics. It's not about learning formulas. Physics is a way of thinking. Now this is a very neat question. I like this question. And the answer to this question lies in your ability to think physically. Yes?
So intensity is the number of electrons per unit area. So the per unit area is increasing, so the intensity will increase.
Yes, so if you, alright. So now what's happening is, if you wait for the same amount of time, the area under these lobes is going, so if you have a fatter lobe, the area under the lobe is large. So if you want to keep the area under the lobe the same as the previous lobe, you have to reduce the thickness. Now the area under the lobe corresponds to the total number of electrons that are received. And if you keep the time of the two experiments the same, you would like to keep the total number of electrons received the same. So you would, if you have fatter lobes, you have shorter lobes. Good. Now the question is, how is the width of the lobe corresponding to the momentum? What does that have to do with the momentum? Let me first answer my own question, then I'll take questions from your end. Suppose this point is P, this point is P prime. Now an electron, if an electron has to reach point P, its momentum must be, it's a vector, the momentum is a vector. The vector must point in a direction that aims at P, right? If it has to reach P prime, its momentum has to point in a direction which aims at point P prime, so that it can move with its momentum and reach point P prime. Now if electrons have to fall within this central maximum, then these momentum vectors are not all aligned in the same direction. There is a fanning out of the momentum vectors from different electrons. So one electron comes in, it has a momentum vector in a particular direction. The other electron comes in, it has a momentum vector in a particular direction. So there is a spread of momentum vectors for the different electrons. Now I'm giving an interpretation, by the way. Don't take this literally, I'm giving an interpretation. So there's a spread of momentum vectors. So if the electrons, all of them have to fall in this general central maximum, and none of them have to go out, none of them are going beyond this, then the spread in momentum vectors is something like this, right? So there's a fanning out, spreading out of the momentum vectors, which means that you don't know what the momentum is. The momentum could be pointing straight ahead, it could be at an angle, another angle, another angle, another angle. In order to achieve this central maximum, the momentum vectors show a spread or an uncertainty. Alright? Now, is the length of all of these vectors the same? Yes, because all the electrons have the same speed. So the length of all of these momentum vectors is the same, they're just pointing in different directions. Alright? Just pointing in different directions. So what we would like to find out is, if this is my x direction, right? I am calling this my x direction. I need to find out the spread in momentums along the x direction. Correct? Now, okay. Now what's the total spread in momentum? So if I take this angle, I'm defining this angle to be theta. What's the x component of this vector? P sine of theta. This is my x component. This is my angle theta. Then so this vector over here can be decomposed into two components. So this vector has an x component px and a y component py. This angle is theta. So this component is p sine of theta. All of these vectors have the same y component because they have the same speed. So delta, alright. Now what about this vector? On the other extreme, we have this vector. Right? So this gives the total range of my px's from here to here, here to here, here to here. So one extreme is px is p sine theta. What's the other extreme? P sine of minus theta, which is minus p sine theta. So what's the total range in my px? 2p sine theta. So my delta px is of the order of approximately 2p sine theta. What is my delta x? So of the order of a. Now what is the product of delta x and delta px? It's 2a p sine of theta. Alright? Now, what is P? H over lambda. Two A H over lambda sin theta. Alright, now one more step to go. One more step to go. By the way, if my delta x goes up, delta px goes down. So if I'm more uncertain about the position, I'm less uncertain about the momentum. If there is less uncertainty about the position, there is more uncertainty about the momentum. So if I reduce the distance between the slits, the central lobe expands. Now I have this relationship. I would like to simplify this slightly further. And what I need to do for that purpose is the following. So let's just look at a single slit. So suppose I just have a single slit and photons are coming out through this single slit, and still I would get an interference fringe, because just imagine that this slit is made up of two small slits. So there is one slit here of length a by 2, another slit of length a by 2. So this one slit can be decomposed into 2 slits, 3 slits, 4 slits, and so on. But I can also have an interference pattern from a single slit. Now what I would like to find out is, if this is my angle theta, the width of this slit is A. Now let me zoom in onto this slit. Let me draw it bigger. So if this were to be point P of my interference max fringe, which means it's a minimum point, then what I need to do is, there should be destructive interference over here, right? Which means that a ray coming out of this location should be exactly cancelled out by a ray coming out of this location, right? It should destructively interfere. A ray coming out here from the slit should be exactly destructively interfering with the ray coming out of this position. So any two rays which are separated by a distance of a by 2 must destructively interfere in order to get a minimum here. So the path difference between any two pairs is given by a by 2 sine of theta, and I multiply this with k, which is 2 pi over lambda. I want this path difference, this phase difference to be equal to pi by 2 if I were to see a minimum here. So now if I do this calculation, this pi cancels out, this 2 cancels out, a sine theta over lambda equals 1/2. So I have this relationship over here. So I just use this relationship, a sine theta over lambda equals 1/2. I just put that 1/2 in here. I get delta x, delta px is of the order of h. This is Heisenberg's uncertainty principle. Now, I would like to end this lecture with an utter surprise. 2 minutes. The next lecture will be devoted to Heisenberg's uncertainty principle, by the way. Now, what's the surprising thing? Now, in science fiction, you would like to say this as the following. In quantum mechanics, an event has already occurred. Sitting in the present, you can change the outcome of an event that has already occurred in the past. Right? This is what is possible quantum mechanically. And I'll have more to say on this, but let me just give you the idea first. Let me just surprise you. The surprise. Everything is just the same. There are only two differences. The screen now is connected to a switch that can take up two values, 0 and 1. It's a binary switch, a toggle switch. And this is an opaque screen. It does not let photons through. Photons or electrons just come and fall on this screen and form a pattern. So no electron or photon or whatever particles we're talking about can permeate the screen. Okay? Now what this switch does is that if it's in location 0, if it's off, the screen is in place. Alright? And if it's in location 1, that I turn on the switch, the screen just shifts out of the apparatus. It goes out. There's no screen. So there's this. It's like a slit. The slit is closed, it's a big slit. You have a motor connected to the screen, and when you turn on the switch, the screen opens and lets electrons or the particles go ahead, right? So you can have the screen in the experiment or out of the experiment. And on the other side of the screen, we have permanently placed two telescopes. One telescope is aimed at slit S2. One telescope is aimed at slit S3. And this distance could be hundreds of kilometers, thousands of kilometers, billions of light years away. This could be a photon or coming from some star, and there could be a black hole in between, and you have two paths of the photons. Alright? So now there's a single electron. And the surprising part, you shouldn't look at your mobile phone. So now what's going to happen is that if the screen is in place, location 0, of course you're going to see the fringes. Nothing has changed because this is an opaque screen. So you're going to see the interference pattern. Now if you switch off the screen, which means switch on the screen, which means the screen goes out of its position, then the interference pattern disappears. Right? Because then you will get in a pattern like this. Now the beautiful thing about this experiment is that if interference were to take place, this screen is so far away that an electron emerging from these slits has already made up its mind to interfere or not. It has already made up its mind. I mean, the interference is taking place inside this region, and this region is so far away in time and in space that this outcome of having the screen in position or not should not affect the interference pattern. Right? Now, this is totally counterintuitive. That is a decision to observe an interference pattern or not to observe an interference pattern is made delayed in time. The choice of having an interference pattern or not is made not while the electron is in the apparatus, but it's made even after the electron has gone through the apparatus. So this is called the delayed choice experiment. So in the delayed choice experiment, you can choose whether interference appears or it does not appear even after the electron has spent ample time inside the apparatus. Please come to 5 p.m. today at the Abdul Memorial Lecture. It's a colloquium by Professor Robert Jaffe from MIT, and he's going to talk about nothing else but time. Thank you very much.